Good evening, students. Today we are discussing about op-amp circuits. Generally, we are discussing op-amp as a comparator in application of operational amplifiers. A comparator is important in circuits where the voltage signals are to be compared and to be distinguished which is a stronger. A comparator is also an important circuit design for non-sinusoidal waveform generators as relaxation oscillators. Op-amp with an open loop configuration with a differential or single input signal as a value greater than 0. The high gain which goes to infinity drives the output of the op-amp in saturation mode. Thus, an op-amp operating an open loop configuration will have an output that goes to positive saturation or negative saturation or switch between positive and negative saturation levels. Thus, the clips the output above these levels. The principle is used to comparator circuit with two inputs and output. Suppose we given the output as given the input as sine waveform, we get the output of comparator a square waveform. The two inputs out of this which reference voltage is compared each other. If the input is given to the inverting terminal and another input is given to the non-inverting terminal, there is a compare between the two voltage levels which is known as a comparator. Another application of operational amplifier, instrumentational amplifier. It is a kind of differential amplifier with additional of input buffer stages. Suppose the circuit diagram shows three operational amplifier. The gain of first amplifier and second amplifier which is added to the third operational amplifier is called an instrumentational amplifier. The addition of input buffer stage make it easy to match the amplifier with the preceding stage. The instrumentation are commonly used in industrial test and measurement application. The instrumentation amplifier also some useful features like low offset voltage and high CMMR, that means common mode rejection ratio, high input resistance and a high gain, etc. The circuit diagram of typical instrumentation amplifier as shown in figure. Here R1, RG, R1 are the first stage of the instrumentation amplifier. The gain will be added to the third operational amplifier which gives the output gain of instrumentational amplifier. Schematic trigger. It is essentially the amplifier which is in positive feedback. It is possible to implement this setup using operational amplifier or simply op-amps. Depending upon the input is applied, the operational amplifier based on the circuits is further divided into inverting and non-inverting schematic trigger. An inverting schematic trigger, the input is applied to inverting input terminal of the operational amplifier. In this mode, the output is produced for positive polarity. That means opposite. We get the output of opposite polarity. This output is applied to non-inverting input terminal to ensure positive feedback. And non-inverting schematic trigger, the input is applied to non-inverting input terminal of the operational amplifier. In this mode, the output is produced as same polarity. This output is applied to inverting input terminal to ensure that negative feedback. The circuit diagram and the waveform representing in the diagram. One of the most important for the operational amplifier, the operational amplifier can generate the waveforms like sine wave, square wave and triangular wave. In that we are discussing sine wave generator. Here we are using 4 resistances and which are getting 4 ohms. One end of arm is connected to resistor and capacitor which is connected in series combination, and another end is connected to parallel combination both resistance and capacitor, and another arm is variable resistance and another arm is fixed resistance. Here variable resistance is represented by RF, that means feedback resistance, and R1 is input resistance. The series combination of R1 C1 and parallel combination of R2 C2 is connected to inverting input terminal of the operational amplifier. Here the circuit said that the periodic electrical signals such as sine wave or square wave. The application of oscillator includes sine wave generator. It is also known as Wien bridge oscillator, the local oscillator for synchronous receivers, and etc. An oscillator consisting of an amplifier and a feedback network. First one is an active device, that is operational amplifier used as an amplifier. Second one, passive components such as RC or LC combination are used for feedback network. We are discussing about passive component in the sine wave generator. To start the oscillations with the constant amplitude, the positive feedback is not only sufficient condition, then the oscillator circuit must satisfy the following conditions known as Barkhausen conditions. First one, magnitude of the loop gain, and second one, amplifier gain, where beta equal to feedback gain. Second one is phase shift around the loop must be 360 degrees or 0 degrees. First, once again repeat. The first one, magnitude of the loop gain. Loop gain is represented by beta, and gain is, that means voltage gain is represented by AV. Here AV equal to operational amplifier gain, beta is the feedback gain, and second one is phase shift around the loop, that means 360 degrees or 0 degrees. One of the most application of the operational amplifier, it is known as a stable multi-vibrator, and it is also called free running oscillator and square wave generator. An astable multi-vibrator is an electronic circuit that generates a continuous square wave output waveform with no stable state. It is known as a free running oscillator or square wave generator. The circuit consisting of two amplifying stages connected in a positive feedback loop. The output of one stage is fed back into the input of the other stage and the vice versa. The result is an oscillating output waveform. The stable multi-vibrator is commonly used in applications such as timers, frequency generators, and clock circuits. The output frequency of this circuit can be adjusted by changing the values of the resistors and capacitors in the feedback loop. The basic circuit diagram of a stable multi-vibrator consisting of two input stages, each of which contain operational amplifier and a feedback network. The feedback network in each stage consisting of resistor and capacitor in one stage is connected to input of other stage and vice versa. Here the input powered by the DC voltage source. Here the circuit shows in the diagram the stable multi-vibrator and waves are representing like this. Here the operational amplifier input is inverting terminal and feedback path is connected in between the terminals output and non-inverting terminal. Here C1 is capacitance and R1, R2 are the feedback and input resistance respectively. Here the operational amplifier gives the input as square waveform which gets the output of triangular waveform. Totally we calculate the time period of oscillations t equal to 2 into t. Here t means time period into log of 1 plus beta by 1 minus beta. Here feedback is representing for feedback path, beta equal to R2 by R1 plus R2. Here representing in the circuit diagram the potential divider at the resistance R1 and R2 is the feedback path. That's why beta equal to R2 by R1 plus R2. Therefore, the total time period of oscillation in a stable multi-vibrator will be t equal to 2 into log of 1 plus beta by 1 minus beta. Here beta means feedback fraction. Triangular wave generator. It consisting of comparator and a integrator. That means The comparator output which follows the input of integrator circuit, the output of comparator will be square waveform, and the amplitude of plus or minus Vset which is applied to the inverting input terminal of the integrator, the output of integrator is a triangular waveform. That means comparator output will be the square waveform, and integrator which is integrated by input voltage, that gives the output of triangular waveform, and it is feedback input to the comparator A through the potential divider R2 minus R3 representing in the circuit diagram. To understand the circuit operation, assume that the output of a comparator A is plus Vset. This forces a constant current, that means Vset by R1. Here Vset means positive saturation and R1 is the input resistance through the capacitance C to give the negative going ramp at the output of the integrator as shown in the below figure. Therefore, the one end of the voltage divider is at positive Vset and another end is negative going ramp. Suppose we giving the input as a positive peak and we will get output as negative peak. When the negative going ramp reaches to certain value of minus V ramp, the effective voltage at point P becomes slightly below the 0 volts, that we get negative feedback, that's which is compared with the value of 0 volts. As a result, the output of a comparator A switches from positive saturation to negative saturation, that means plus Vset to minus Vset. This forces a reverse constant current through capacitance to give the positive going ramp at the output of the integrator. The waveform is representing as shown in the figure. The figure shows the positive going ramp reaches to plus V ramp. The effective voltage at point P becomes slightly above the 0 volts. As a result, the output of comparator switches from negative saturation to positive saturation, that means minus Vset to plus Vset. The sequence will repeat the similar way. We get a triangular output of the integrator B. The waveform is representing here, the square wave is input waveform and the positive peak representing in the waveform the output waveform which goes positive V ramp to negative V ramp. In our input, the square waveform in negative saturation, in output the negative saturation will be converted into positive V ramp. That means one complete cycle of this triangular waveform which get from positive peak minus Vset to plus Vset and plus Vset to minus Vset. Then we calculate the time period of oscillation of triangular waveform. Then it will be reciprocal. The frequency of oscillation will be calculated. Therefore, the frequency of oscillation can be representing F naught equal to 1 by T, that means R3 by 2R1 C1 into R2. This is the frequency of oscillation. We can calculate it. Active filters. Filters means nothing but the electronic circuit which allow certain frequency components or reject same. They are passive and they are electrical circuits or networks that consisting of passive network or passive elements like resistor, capacitor and an inductor. There are 4 types of active filters we are discussing. One is low pass filter, second one high pass filter, third one band pass filter, fourth one band stop filter. Active filters in the electronic circuit which consisting of active elements like operational amplifiers along with passive elements like resistor and capacitor. The active filters mainly classified into 4 types based on the band of frequencies that they are allowing or rejecting. First one is active low pass filter, second one is active high pass filter, third one is active band pass filter. In active low pass filter, if an active filter allows only low frequency components and rejects all other high frequency components, then it is called active low pass filter. We know that electrical network which is connected to the non-inverting input terminal of the operational amplifier is a passive low pass filter, so that the input of non-inverting input terminal of operational amplifier is the output of passive low pass filter. Observe that The above circuit assumes that a non-inverting input amplifier, it is having an output of passive low pass filter as the input of non-inverting input terminal of the operational amplifier. Hence it produces the output which is non-inverting of the voltage gain 1 plus Rf by Ra. Here Rf is the feedback resistance, R1 is the input resistance, and the input is present in the non-inverting input terminal. We can choose the values of Rf and R1 sustainably in order to obtain the desired gain of the output. Suppose we consider the resistance values of Rf and R1 as 0 ohms and we get the output as 0. Then the above circuit will produce the unity gain of the low pass filter output. Here the circuit diagram shows in the low pass filter of operational amplifier. Here Rf is the feedback resistance, R1 is the input resistance, and capacitance will be grounded to the non-inverting terminal. Here the graph is shown, frequency on x-axis, output voltage on y-axis. Here the cutoff frequency will be calculated. The maximum voltage obtained at 0.70 times of its maximum value, then it is called cutoff frequency. The below the cutoff frequency is known as pass band and above the cutoff frequency is known as stop band. The frequency lies between frequency and output voltage as shown in the figure. Here the low pass filter, the circuit diagram is shown in the slide. If an active filter allows or passes only high frequency components and rejects all other low frequency components, then it is called active high pass filter. The circuit diagram of an active high pass filter as shown in the below figure. We know that an electronics network which is connected to non-inverting input terminal of operational amplifier is the passive high pass filter. So the input of non-inverting input terminal of operational amplifier of the output of passive high pass filter. Now the above circuit resembles the non-inverting input terminal of operational amplifier. It is having the output of passing high pass filter as an input to non-inverting input terminal of operational amplifier. Hence it produces an output which is the operational amplifier of the gain, nothing but 1 plus Rf by R1, the input present at the non-inverting input terminal as shown in the above figure. We can choose the values of Rf and R1 suitably in order to obtain desired gain of the output amplifier. Suppose we consider the resistance values of Rf and R1 as 0 ohms and infinity ohms. Then the above circuit will produce unit gain high pass filter output. Here the graph shown in the figure, here the above the cutoff frequency is known as pass band and below the cutoff frequency is known as stop band, which is the cutoff frequency can be calculated the maximum voltage which falls from 0.70 times of its maximum value of an output voltage. Another one high pass filter, another one filter, band pass filter as shown in the below figure. If a filter allows passes only one band of frequencies, then it is called active band pass filter. In general, this frequency band lies between low frequency range and high frequency range. So active band pass filter rejects both low and high pass frequency components. In low pass filter only high frequencies are rejected which passes only low frequencies. In high frequencies, in high pass filter only high frequency components are which allow and rejecting low pass filters, low frequency components. But in band pass filter we get both low and high frequencies are rejected by the band pass filter. The circuit diagram of an active band pass filter as shown in the figure. So we can observe that there are two parts in the circuit diagram of active band pass filter. The first part is an active high pass filter while the second part is an active low pass filter. The output of active high pass filter is applied as an input of active low pass filter. That means both high pass filter and both low pass filters are cascaded in order to obtain the output in such a way that contains only particular band of frequencies. The active high pass filter which present in the first stage of allows the frequency that are greater than the lower cutoff frequencies of the active band pass filter. So we have to choose the values of RB and CB suitably to obtain the desired lower cutoff frequency of the active band pass filter. Similarly, the active low pass filter which present at the second stage of allows the frequencies that are similar than the higher cutoff frequency of the active band pass filter. So we choose the values of RA and CA suitably in order to obtain desired higher cutoff frequency of the active band pass filter. The figure shows the graph. The graph shows the active band pass graph. Here frequency on x-axis and output voltage on y-axis. The figure representing below the cutoff frequencies. Both below the cutoff frequencies are representing for stop band frequency, and above the cutoff frequencies are known as band pass frequencies. Here the lower frequency FL represented by FL and higher frequency is representing by FH. The bandwidth of the band pass filter will be the difference between two frequencies that are called high frequency minus low frequency is known as band pass filter. The last topic of this unit, IC 555 timer. Here the block diagram representing for IC 555 timer. Here the pin 1 is representing for ground and pin 2 for trigger and pin number 3 for output voltage and pin number 4 for reset and pin number 5 for control voltage, pin number 6 for threshold voltage, pin number 7 discharge and pin number 8 will be the plus VCC. Here the block diagram representing like here upper comparator, lower comparator, two comparators are connected to RS flip-flop, then it will be connected to inverter and the transistor representing in the block diagram. Here the pin 1, ground pin. Ground pin directly connected to the negative terminal of the power source. It is suggested that it should not be connected using any resistor because all the IC will be heat up due to stray voltage. That means the occurrence of electrical potential between the two objects that ideally should not have any voltage difference between all. That means all pins will be going to ground terminal which current flows in the circuit. Second pin, trigger pin. The trigger pin is used to activate all IC timing cycle of operating voltage. It is a low signal pin and the timer is triggered when the voltage is below 1/3 of the supply voltage, that means 1/3 volts. It is connected to the inverting input terminal of the comparator inside the IC and accepts negative signals for the operation. The third pin will be the output pin. The output pin will get the output of the output of the IC 555 timer. It is an output pin. As the IC triggered, the output pin goes highly depending upon the duration of the timing cycle provided to it. In the case the logic 0 output, it is sinking current with voltage greater than 0, whereas in this case of logic high output, it is sourcing current with the output voltage lesser than the 0 volts. Fourth pin, a reset pin. The reset pin is used to reset. It should be connected to the positive terminal of the work of IC properly, which is grounded. The IC would work at all the required reset voltage 0.7 volts at the current rating of 2 milliamps to work. The pin number 5 is representing for control voltage. It is used for reliable operation. When not in use, it should be connected to the ground through the capacitor. Otherwise, the IC will be show erratic response, that means deviating from the desired value. Pin number 6 is representing for threshold pin. It detects when the voltage on the timing capacitor rises just above the 0.66 of 1 by 3 of VCC, the timing cycle is only completed when the voltage on the particular pin is equal to or greater than 2 by 3 of VCC. The pin number 7 will be the discharge pin. It is used to provide the discharge path of timing capacitor to the ground when the output is low. The discharging current should be less than 50 milliamps in order to prevent it from the damaged one. The last pin of the IC 555, that is the power supply terminal, that means plus VCC. It is a positive terminal that is connected to the positive terminal of the power source in order to power up the IC 555. It is used to take power supply voltage from the power source for operating the IC 555. This is about IC 555. The last topic of IC 555 we are discussing of applications. It is used for pulse, waveform and square wave generation. It is used for time delay generation and precision timing and sequential timing. It can be used as monostable multi-vibrator or a stable multi-vibrator. The IC 555 mostly used in pulse width modulation and pulse position modulation circuits, used in tachometers and temperature measurements. They are commonly used in DC voltage regulators. It is also used for conversion like voltage to frequency converters, mainly used in detection circuits in FM. It is also used in frequency divider. It is also used in pulse detector. It can be used to design a timer switch. This is all about IC 555 application.